Okay, a couple of announcements. While you get your iClickers ready, I'm gonna ask you a few questions. We have the second midterm this Friday. I will send out instructions like I did for the first midterm by email, probably tomorrow. But the format is, like I said the other day, essentially the same. Same type of exam with a mix of multiple choice questions and simple problems. Does anybody have a question? And then, so that's on Friday, and the Wednesday, so the next lecture in 2 days, I will do a review. A short review of what you should be preparing for and so on. Okay, so let me, if you get your clickers ready, I'm going to ask you about 4 questions. These questions pertain to the previous lecture, so before I go into the next section of the chapter, I want to make sure that we cover some of these important concepts. All right, so there is your first question. For a velocity potential to exist, the flow must be, pick one answer. Didn't find it yet. Okay. Closing it. 3, 2, 1, 0. So for a velocity potential to exist, the flow must be, wow, okay. So the correct answer is C. The flow must be irrotational. Is the only condition that is needed for a flow, for a velocity potential to exist. Only one condition, that the flow be irrotational. Let me go to the next one. Let me just go through the 4, and then if there are questions, I'll ask at the end. So now we have an incompressible and irrotational flow. It's both incompressible and irrotational. The equation Laplacian of phi equals 0 represents one of those 5 answers. Found it? Not yet. Right. Okay. Closing. 3, 2, 1, 0. That is the correct answer, C. It represents conservation of mass. Again, it's in the lecture. If you go through the derivation of that equation in the lecture, it comes from applying the equation of conservation of mass for an incompressible flow with the existence of a velocity potential. And these are all, by the way, good practice questions for the exam. Essentially the same question, but I replaced, now I'm talking about the Laplacian of psi equal to 0. Again, for an incompressible and irrotational flow, Laplacian of psi equals 0 represents, and in fact it's the same 5 answers as in the previous question. All right. Did you find it? Huh? Didn't take good notes. Okay, so closing 2, 1, 0. Okay, and the correct answer is B. It comes from the condition that the flow is irrotational. So essentially, you know, if the flow is irrotational, the vorticity is equal to 0. You look at the expressions for vorticity. You only need to look at one because it's a two-dimensional flow. And then you plug in the expressions for psi into that expression for vorticity and then set it equal to 0. And that becomes the Laplacian of psi equal to 0. Okay, so now we still have a constant density flow, but I want both phi and psi to exist. What conditions are required for this constant density flow in order for both phi and psi to exist? Okay, so last few in. Two, 1, 0. Okay, so now I want both phi and psi to exist. So therefore I want the conditions for both, for psi to exist and for phi to exist. So for psi to exist, I need the flow to be two-dimensional. And for phi to exist, I need the flow to be rotational. So D is correct. Okay, and that's the last one. Okay, so while people find their seats, does anybody have a question about any of these questions or anything related to this?
I guess the first one, so it just needs to be irrotational because the density is constant, though, isn't it?
The first question was, let me go back. For a velocity potential to exist. No, there's no condition on whether it is a constant density or not. It doesn't matter. The only condition required for a velocity potential to exist is that the flow be rotational. Let me show you where that comes from last time. It's essentially the result of a mathematical identity. And it's in this box, in the first box on the top. So the first line, of course, is the condition of the flow being irrotational. The curl of V, or the vorticity, has to be equal to 0. And this that I put on the right-hand side in red is a mathematical identity. That is, if you have a function, a scalar function, phi, and you take first the gradient and then the curl, the result is always 0. So because of that, then if I simply substitute that in here, then of course I want the gradient of phi to be the velocity. So the velocity potential appears just from the condition that the flow be rotational. Any other questions about the questions of the material in the questions? Okay, then let's move on. So now that we have learned the meaning of the velocity potential, and we already have the stream function also supposedly mastered, it's time to look at what we call basic potential flows. So now we know all these features of potential flows. Potential flows have to be rotational. If we want to use a stream function in connection with a potential flow, then we also want the flow to be two-dimensional. So there are 4, you may argue 5 if you consider the second line too, but 4 basic potential flows that we study. And they're listed here. Uniform flow, we've talked about it a few times. Source and sink, which probably will be new to you. Vortex, also a new one to you, and the doublet. So today, I am going to cover these 4 basic potential flows. And just to give you a hint of what's going to happen next, which will be, of course, after the midterm, we're going to combine these basic potential flows to obtain flow fields that start to have some real physical interpretations or can represent some real physical situations. So to summarize, we're going to be looking at two-dimensional flows, constant density, that will allow us to introduce the stream function. So we're going to be looking at constant density flows, which are two-dimensional, so we can use psi. And because we're talking about potential flows, we also want the flows to be rotational, so phi is equal to 0. So then we know that 2 of the questions today, that both psi and phi must satisfy Laplace's equation. So we just need to study some specific functions, psi and phi, that satisfy Laplace's equation and represent some basic potential flows. The first one is one that we have already seen before, is the uniform flow. And a simple schematic of it is, for example, if I pick the flow to be in the x direction, then I just have a flow where the velocity is the same everywhere. It's a constant speed u naught. And in this case, it's moving in the positive x direction. So every fluid element is doing exactly the same thing. And therefore, the fluid elements are not deforming. They're just translating to the right. They're not rotating, so it's irrotational. It's a very simple flow. So the first question that we ask ourselves, well, what is the stream function and what is the velocity potential for this uniform flow? And the way we get the answers to those questions is simply by using what we already know about how the velocity potential and the stream function are related to the velocity components. So for example, earlier we learned that the horizontal velocity component u is the partial derivative of psi with respect to y. I have that from before. And then more recently we learned that from the definition of a velocity potential that same horizontal velocity component is partial phi, partial x. So there I have 2 equations that tell me something about phi and something about psi. And I can also write down the equation for the other velocity component, which in this case happens to be 0. So the v velocity component is 0, but I knew from before that that was equal to negative d psi dx from the definition of the stream function, and from the velocity potential, v is also d phi dy. So those conditions are sufficient to build the stream function and the velocity potential by simply integrating those equations the way I did it last time in one of the examples that I solved here. So if I simply take those equations and I integrate them in x and in y, and then maybe also the other one in y and in x, the order doesn't really matter. You can integrate it using the same technique we used last time. Then you find that the velocity potential is the constant velocity u naught times x, and the stream function is the constant velocity u naught times y. There are constants of integration that come up that we saw in the examples from last time. So there would be a plus some constant here and plus some other constant there. But I told you that those constants are not relevant because they disappear upon differentiation when we're trying to find u and v. So those constants essentially add a constant factor to these functions, but they are not relevant for the flow field. So there they are, not surprising, that's what they are. And so if we plot lines of constant psi, what do those lines look like if psi is constant? What are lines of constant psi? What? Yeah, but what do they look like? Like they were on the figure, right? Lines of constant psi would mean lines of constant y, and therefore those are lines of constant psi. We know that because the lines of constant psi should match the streamlines. What about lines of constant phi? What do those look like? They'll be vertical lines. So if I plot them for uniform flow, that's what I'll get. This is a neater plot, but it's essentially the same thing. The blue lines are the horizontal lines. Those are lines of constant values of psi. For example, I can label them psi 1, psi 2, and so on. And then the vertical lines where phi is constant, I can label them phi 1, phi 2, and so on. And they're vertical lines. So I get this perfectly rectangular grid representing uniform flow, moving to the right. So that's fairly straightforward, I think. Remember, we call these vertical red lines the equipotential lines. It's lines where the velocity potential is constant. And of course, we call the horizontal lines streamlines. So what happens next? Let's think about the source. So let's actually start it from scratch. So here is a coordinate system, say for example x and y. And the source, for you to visualize the source, think of suppose you have a very long and narrow garden hose or a pipe. Very long, very narrow, very slender, so really you don't have to worry too much about its diameter. And there is fluid going through it, but suppose you were able to drill very many, in fact, infinitely many holes all around this tube, okay? So that when the flow is going through the pipe with pressure, it's just going to spray out radially in all directions. So if I look at that and I place my line, which is really what we call a line source, if I put it perpendicular to the board and I look at the flow field that it generates, all I would see is many lines like that where the fluid is being radially sent in all directions. Right? So of course we're not thinking about gravity changing anything, just the very thin line source capable of spraying water in all radial directions. That's what we call a source. To be more specific, we call it a line source for the reasons I just gave. Otherwise, it wouldn't be two-dimensional. So we want it to be two-dimensional. We make it a line source. If it were a point source, so no longer a line, but just a point which throws water in all directions, then that would be what we call a point source, but then that would be a spherical distribution. We just want it to be two-dimensional. So that is what we call a line source. So the question is the same. And of course, if I do the opposite, if the line, instead of being a source, is what we call a sink, so that it draws in all the fluid from all around it, all I have to do is reverse the directions of these arrows, and then I have a line sink. Right? So the line sink is just the opposite of a line source. Radial flow, but incoming into the origin. And so that we ask ourselves the same question: what is phi and what is psi for a line source? We should be able to immediately say what they look like in the plot, because the blue lines are, in fact, streamlines, and therefore the blue lines are lines of constant psi. Right? All of these lines, if I extend them to make it a little bigger, right? Those are, in fact, I could label them, for example, this actually is going this way. I could label them psi 1, psi 2, psi 3, and so on. As I go around. Those are lines of constant psi. So what would the lines of constant phi look like? It's very easy and very obvious. They'll have to be circles. So these lines, right, would be the equipotential lines. So let's make this red. The equipotential lines, they'll be circles. But now can we show it mathematically? That is, can we use the definition of a stream function and the velocity potential to do this? And the answer, of course, is yes. So I could do it a couple of different ways. Let me actually show you what we want. If I were to ask you, well, what should U sub r be? Can you give me an idea of what U sub r? I need to work in cylindrical coordinates, obviously. So what U sub r would be and U sub theta would be for this flow. You can start with either one. What's U sub theta? I've asked you many times during the quarter, haven't I? Well, let's ask the lady next to you. What is U sub theta for this flow? Anybody wants to help her? U sub theta. Yeah, it is constant, but no? 2 pi? Wild guess. Anybody else? What is U sub theta? 0. Where's the flow going? It's all going radially out. So yeah, it is a constant. The constant is 0. It's all radially out. There is no flow going in the theta direction. So I was hoping that one would be obvious. There is no U sub theta. U sub r is a little harder. What would you say U sub r is? That's a little harder. You have to think a little bit more. Anybody has an idea what U sub r might be? This one I don't expect you to have an idea. So let me tell you the following. Suppose I do something a little bit different. Suppose that I tell you that this is the velocity potential. I claim that whether it's a source or a sink will depend on a sign, but suppose that I claim that that is the velocity potential. m is a constant. We'll find out what that constant means in a moment. But m over 2 pi is just a constant. So it's a constant time the natural log of r. That's I claim that's the velocity potential. First thing we could check is, well, are lines of constant phi circles? If that is the velocity potential? Are you convinced that lines of constant phi are circles? Yes? Why? Where are you convinced?
From the line source?
Yeah, but tell me a little more. If I say that phi is constant on circles, is that true? Are you convinced? Are you convinced? You guess. Okay, so if I want phi to be constant, so this has to be a constant. What about r? It has to be a constant, right? Because everything else is a constant. So if phi is to be a constant, then r has to be a constant. And r equals constant is what? A circle, right? R equals constant is a circle. So at least this satisfies that equipotential lines, as I drew them in red, are circles. All right, so let's find out what the velocities would be according to this. And a while back, a few lectures ago, maybe only a couple of lectures ago, maybe last lecture, I told you how to find the velocity components in cylindrical coordinates. So for example, if you want to find u sub r in cylindrical coordinates from phi, all you do is partial phi, partial r. In fact, that's very similar to the way you would find them in Cartesian coordinates. U sub x, for example, in Cartesian coordinates is partial phi, partial x. Well, u sub r is partial phi, partial r. So if I just take that expression that I propose for phi and I take the derivative with respect to r, I get m over 2 pi r. As the velocity. That's the velocity of the flow as it moves radially out from the line source. So I can make a couple of observations about that velocity. What happens to that velocity as I move from the line source radially outwards? It decreases. So as I move farther away from the line source, it decreases. What happens at the line source is infinitely large. That's what we would call a singularity. Right? There is a singularity at the line source. The velocity is infinitely large at the line source. Why is that happening? Because remember, I said, let's picture this to be like a pipe, a long pipe with many holes that is shooting water out. I said something else about the pipe. I was going to make it very, very small, very narrow, very small diameter. So essentially what we're looking at is what would happen if the diameter were to shrink to 0. Then the velocity would have to go to infinity. But if you think that it actually has some real diameter, then you don't start from 0, you start from the real diameter, and you don't have the problem of the singularity. But if you take it all the way to 0, then you have a singularity. Okay, so, and then likewise we can say that u sub theta, from the expression for u sub theta, is 1 over r d phi d theta, and of course my phi doesn't depend on theta, so that's 0. So those are the velocity components. U sub theta is 0, u sub r is m over 2 pi r. So the schematic we already looked at. I could build backwards to build the stream function, because I'm saying that's phi. But suppose that I ask you, if I give you phi, find the stream function for me, then you do the integrations backwards. So you say, well, I know that u sub theta is minus this psi dr, and I know that u sub theta is 0. And then at the same time, I know that 1 over r d psi d theta is u sub r, and that was given, or we just found what that is, rather, m over 2 pi r, so I can integrate it. And then I find that psi is m over 2 pi theta. And I can ask you the same question. Are you convinced that these are indeed radial lines? When psi is constant, how do I know these are radial lines? Because if psi is constant, theta has to be constant. And a constant theta means a radial line. in cylindrical coordinates. So this has the properties that we expected. Equipotential lines are circles. Streamlines are radial lines. The only thing that is new that we didn't talk about in the original figure was that the velocity decreases with radial distance. Why does that make sense, or should make sense, that the velocity decreases with r?
It's coming from your source, so you're interacting with more.
No, it's not exactly that. The velocity decreases as I go radially out. No, it has nothing to do with pressure. Okay, so yeah, so that's true. As I go out, the flow, this one is a sink, so I have it drawn in, but if we look at the previous one, it goes through a larger area as it goes out. So then what? Mass conservation. The velocity has to be lower so that it matches the increase in area, and the actual flow rate is constant. Otherwise, somehow you would be making new mass. Right? So the mass all came from the line source, is spreading radially outwards. It has to decrease in velocity so that mass is conserved. We can, in fact, compute the mass flow rate. So here is the same situation. The question you can ask yourself is, draw a line, in this case, this black line here, and find out how much flow, how much mass is crossing this circle. So for a given circle, for a given equipotential line, how much fluid is crossing that circle? And then you do it well. The mass flow rate crossing that circle will be rho times the velocity times the area. The area would be the perimeter, which is 2 pi r. And of course, that's per unit depth. Because remember, we're looking at a two-dimensional problem, so everything is going to be per unit depth. So if I do that, m dot equals rho times ur times 2 pi r. And now we bring in what we just said about the u sub r. U sub r is m over 2 pi r. That's exactly what you need to cancel the r dependence from the area. So the r's cancel out. The 2 pi also happen to cancel out for convenience. And then you just get rho times m. That would be the mass flow rate per unit depth. And it's constant because it doesn't depend on r anymore. So what's the little m then? If this is the mass flow rate m dot, what's the little m? What's little m? Is the volume flow rate. Is the volume flow rate. An unfortunate choice to call it m, but I decided to stick with the notation in the text. So I would probably maybe call it q, because we have called volume flow rate q in the past. But anyway, if m is then the volume flow rate, of course the volume flow rate per unit depth times the density is the mass flow rate per unit depth. So m is the volume flow rate per unit depth, and we find that m dot is constant for any r, as we expected from mass conservation. So whatever is crossing a certain circle, whatever mass flow rate is crossing a certain circle, that same mass flow rate is crossing a wider circle, a bigger circle. There is no mass created or destroyed between two of the circles. Right? So that is the source, the line source, or its counterpart, if it goes the other direction, the line sink. All right? The next one on my list, unless there are questions about the line source, the next one on my list was, which one? The third item on my list was a vortex. So very simple to create it. Suppose you have this sink that we were just looking at. The sink had radial streamlines, circles as potential lines. Suppose I reverse their role. Suppose I now say that the circles are the streamlines. Right? The circles are the streamlines. Then the radial lines have to be the equipotential lines. So if I just reverse the roles of phi and psi, right? Now I got fluid going around in circles around the center. Again, properly you would refer to this as a line vortex. So it's still a line perpendicular to the paper at the origin, but the fluid is just going around that center. So now the constant psi lines are circles and the constant phi lines are radial lines. So that's all we do to create the vortex out of what we have for the source and sink. So now this would be, if you think about it, if I'm reversing the roles, right? Now U sub r is 0. Right? There is no fluid going out in any radial direction. No U sub r. And U sub theta is some constant that I call k here over r. Remember, for the source, it was the opposite. If we just bring this here for a moment to compare at the bottom, right? For the source, the theta velocity was 0, and the radial velocity was some constant, which happened to be m over 2 pi divided by r. And now is a constant divided by r is the theta velocity. Right? So role reversal with respect to the source. So I can do the same thing, go through the same equations to find phi and psi through the definitions of phi and psi, and I would find essentially the opposite, that now the constant, or the function phi, the potential function, is some constant times theta, whereas the stream function is some constant, it happens to be negative, times the natural log of r. So again, if you compare these to the previous result, you'll see that they flipped nature. So for the source, phi was a function of the natural log. Now psi is a function of the natural log. And for the source, psi was just a function of theta. And now phi is a function of theta. The choice of what you call the constant is different, but it's really a constant. So now we call it k instead of m over 2 pi. But the functionality has been reversed. So that's the vortex, or the line vortex. So this brings in a new concept for you, which is the concept of circulation. And circulation has to do with the fact that this fluid is going, like I said, it's going around in circles. So if I pick a point here, and I look at a fluid element, for example here, what is that fluid element doing? It's just going around in circles. We don't know yet what's happening if it has vorticity, or should it have vorticity? Should that fluid element have vorticity? No, because otherwise it wouldn't be a potential flow. So we could find out, we know what the vorticity is. And the formation? Nothing prevents a fluid element from being deformed in a potential flow. The only requirement is that it has no vorticity. But we know it's going around. What is happening to its shape, we don't know yet, but it's just going around. So that going around feature of the flow is what brings in the concept of circulation. So circulation is a measure of how much the fluid is going around. So I'm going to give you a definition that is very general, not just for this flow field called the vortex, but for any flow field. So there is a flow field. There is an arbitrary flow field represented by those black streamlines. And suppose that I draw an arbitrary loop. So that I look at my flow field and I draw an arbitrary loop, but it has to be a closed loop anywhere in that flow field. So that's what the red loop represents. I just have to make it a closed loop. And the concept of circulation is precisely, let's find out if the fluid, if I go around this loop that I drew, if I go around this loop, whether there is fluid that is going around that loop. If there is any fluid going around that loop, then I say that there is a certain amount of circulation around that loop. So how do I find, as I go around the loop, how do I find if there is any fluid going around? Well, I take a segment of the loop right there, ds, and there will be a velocity field at that position in some arbitrary direction like I drew it there. So what I do is I take that velocity vector and I form the dot product with a vector that represents the length of that segment, ds. And therefore that vector is parallel to the segment. So if I think of a short segment, I take it short enough so I can think of it as being straight because it's very short. And I take the dot product of v and ds, what am I really doing? I'm taking the component of the velocity that is lined up with that segment, right, ds. That's when I take the projection of the velocity on ds. Right? So I just take that. It's different from what we did before when we did v dot n, because that n was what? Normal, but what kind of a vector? A unit vector. Right? So we were just taking the component. If I just do v dot, some unit vector in the direction of the segment. So I'm also multiplying by the length of the segment. Right? So I'm taking the projection, but also the length of the segment. So if I do that, v dot ds, and I just do it for the entire loop. So I just go to the next segment and the next segment and the next segment and I add them all up until I go back to the starting point. Then of course what I have is a loop integral of v dot ds. So when I am finished, when I go back to the starting point, and if I get a value that is not 0, then I found that around the loop that I drew, there is circulation. So, and then we call it gamma. So gamma is the circulation around any closed loop. So that's just the definition. So now, what happens in our flow field? So now that was for any flow field, but now what happens if I apply that concept to any of these circles? So the loop, instead of being any loop, I'm going to take a loop around one of those circles. So pick a circle and find the circulation. So the calculation is here. So let me start little by little here. So I take, at a certain radius, I take my segments, I pick that line or that circle that is in red, the outermost circle, and I take a little segment. So I do velocity dot ds. So what is the velocity? Remember, it was k over r from the previous page. The velocity was k over r. And the length of that segment ds that I drew here in red, the little segment in red, do you agree that is r d theta? Right? And theta, of course, is, or d theta is this angle right there. If I draw it here, that's my d theta. So the product of r, the distance that I am from the center, times d theta gives me the segment. And what about the dot product? V dot ds. Yeah, I know what you mean. The angle is 0, because both the velocity and the ds are in the same direction. That's just convenient in this case. The loop happens to be in the direction of the flow. So this is the full velocity. So if I do that, see what happens. So since the velocity is k over r and the segment length is r d theta, then the r cancels out. And I just get the constant which I can pull out. And how do I describe a full loop? By doing the integral from 0 to 2 pi. So I do the integral from 0 to 2 pi. And I just get the constant, and the integral, of course, is 2 pi. So I get 2 pi times k. Even though I wrote k times 2 pi, right? And so I find, yes, there is circulation around the loop that I took at some distance r. There is a circulation, but the result that I got is independent of the distance. So what that means is that the circulation is the same on any circle. So if I go around a small circle, I get the circulation of 2 pi k. If I go around a bigger circle, I also get circulation 2 pi k. All right? And that is the vortex and the concept of circulation associated with the vortex. Any questions? Okay, let me tell you a little bit about the next one, but I won't have time to go through the whole thing. But suppose that I'll just finish after in the next lecture, because in fact, it is a combination. So the idea is that the next one on my list was the doublet. So let's just discuss a little bit how a doublet is created, and then go through the details next time. So the idea here is, suppose that I have, here's my coordinate system, x and y. We learned about the source, right? And we learned about the sink. When we studied the source, where did I put the source? So there was the source. I put the line source at the origin. All right? So I'm going to do the following. I'm going to put a line source, but instead of putting it at the origin, I'm going to move it to the left some distance, and I'm going to put it right here. That's my line source. Right? And now I'm going to take a sink, which I also put at the origin, because I just told you that the source and the sink look the same, just reverse the flow field. I'm going to put the sink a symmetrical distance to the right. All right. I'm going to put a line source on to the left side, and let's say that I call this distance A. From here to there, this is A, and of course this is also A, negative A, but it's same distance. So now I have this source on the left and the sink on the right. What will happen? Suppose I don't have the sink. If I don't have the sink, well, this behaves like any source. It just shoots water out in all directions, right? Right? And the sink behaves like a regular sink. It takes water in, or fluid in, from all directions. Right? So of course, if you're very close to the source or very close to the sink, you don't really know that the other one is there. But when you get somewhere in between, then what happens? So suppose you are a fluid element that comes out of the source. You are this fluid element that came out of the source. Where is that going to go? It's going to go into the sink. Right? We can intuitively think that if I follow the path of that fluid element, let me draw it in red. If this sink weren't here, it would just go straight out like a regular source. But as soon as it starts feeling the pull from the sink, it's going to go in there. Right? And of course, I can say the same thing about the one back here, I can say the same thing about this one, I can say the same thing about this one, and so on. So now I have combined a source and a sink at a certain distance apart. And you can figure out what happens to some of the other elements. So the doublet, and we'll talk about it next time, is suppose that I now take this source and this sink and I start bringing them closer and closer together. What happens? I'll answer that question next time.